today we are going to talk about the law of sines, and we already talked a little bit about it and how we can get that ratio, like sine of angle A over side A. Basically, that the ratio of the sine of an angle over the side across from it is equal for all three angles in the triangle. Okay? But then we talked a little bit before we left about the fact that I could have been deceiving you with certain instances of information because maybe there wasn't a triangle at all. So we're going to talk a little bit about that. So as you see at the beginning, when solving for a triangle, one of the following will be true. Either no triangle exists, so there's no solution. One triangle exists, and there's one unique solution, meaning you can solve for one set of sides and angles in that triangle. Or two triangles exist, and you need to get both of those solutions. Okay? So what we're going to do is we're going to go ahead and look at these different situations. So before we put something on your note guide, the last part you can be, when it's called two solutions, this is called the ambiguous case because you're unsure. And so we're going to talk a little bit about that situation. And see what that looks like. So I first just want to point out the fact that the times when you have to be aware of this is like we were talking about in class previously, that like angle side-side situation. So what we're going to do is we're going to use angle A for our formula. So it's basically like this is all based off of this triangle ABC. Now you know the letters can change. So as we use A's and B's and stuff like that, be aware of what they really mean, like, oh, that's an angle on the side across from it, or that's an angle on the side next to it, so that we understand fully that they could change the letters and we can still get this okay. So what we're going to look at is where they give us information about an angle. We're going to specifically use angle A, the side across from it, and a side adjacent to it. So that's the angle side-side set of information. See these pieces here. Okay? So if we have that information, how can we tell if there's one triangle, no triangle, two triangles? So first, I want to point out that if we have this triangle, remember this side, we don't know how long it is. Nobody's dictating it. We can find that on our own. But they are setting this angle and this distance here. So this angle is set at a certain amount of degrees, and this distance is set. Okay, and we're going to call that side B. If A is bigger than B. So that's the first thing I'm going to check. So you might want to write these at the top of your paper. So if the side across from the given angle is bigger than the side adjacent to it, then you know for sure that you just have one solution. And the reason for that would be if I look at this situation where this angle is set and the side length B is set. If A is longer than B, there's no way that A can go back at this angle because it'd be longer than B, so it'd have to extend way over here, and that's not the direction that the line goes. So that can't be A if I know A is longer than B. So what I do know then is that there's exactly one triangle, because I also know A is not too short right here because it's already longer than B. So there's going to be exactly one triangle where I can fill in side length A, and then I can use my law of sines to finish finding the ratio. Okay, so the first situation is if they give me information and the side across from the angle is longer than the other given side, then I know that I have one solution. The second situation, if they give you the same set of information, and again, this set of information is an angle, like angle A, the side across from it like side A, and a side next to it like side B. Let's say in your given information, the angle that they gave you is bigger than or equal to 90 degrees. And again, this is just kind of summarizing some stuff from geometry that we know to be true. If the angle is bigger than or equal to 90 degrees, then we have to look at the side lengths, and two things could happen. Either the side across from it could be less than or equal to the side next to it, or the side across from it could be greater than the side adjacent to the angle. So let's think about that. Okay? If we knew that the given angle was bigger than or equal to 90 degrees, so I'm going to go ahead and make an obtuse angle here. So if I knew that this was bigger than or equal to 90 degrees, so let's say it's out there, and that's side B now. Okay? And then I look at the comparison between side A and side B. So here's side B. Here's angle A. It's bigger than or equal to 90 degrees. Now, whether that angle is bigger than or equal to 90 degrees, it is the largest angle in the triangle because a triangle can only have 180 degrees, which means this side across from it that would be necessary to complete the triangle, side A, would have to be larger than side B because it's across from a larger angle. So in these two scenarios here, so if our angle is bigger than or equal to 90 degrees, we then look at the side measurements. Angle A being bigger, side A being bigger than side B is what we said had to happen. So if that relationship is true, then there is one triangle, one solution. However, if they give you a measurement for side A, over here across from the big angle, that's smaller than or equal to side B, that doesn't work because that means that angle A and angle B would either be equal or angle B would be bigger than angle A, and we know angle A is the biggest angle of the triangle, so this relationship doesn't make sense. So there would be no solution. Okay, so again, let's summarize. The first thing we're going to check is if the side across from the given angle is bigger than the side adjacent to it, and then we know we for sure have one triangle that can be formed. If we don't have that information, we're going to move on, and we're going to look at the angle. If the angle is bigger than or equal to 90, again, it better be true that angle A is bigger than angle B, which should have shown up in the first step, so that we do have one solution. Otherwise, if it's this situation where A is less than or equal to B, that does not make sense with an angle A that's bigger than or equal to 90, therefore giving us no solution. Okay? So then this leaves us, what if it doesn't fall into these cases? So that means, what if A is not bigger than or equal to B, like the first case, so A is less than B, and angle A is less than 90 degrees. Okay? Then we could have no solution. We could have one solution. And we could have two solutions. And we're going to look on our note guide about how to make that decision. So again, we're going to check these two things first because they're a little quicker and easier to understand. And then if none of those things is true, we're going to move on to check this third thing and decide which situation we are in. So going back to your note guide, okay, remember if we build this triangle, and again I'm calling this angle A and this side B, which is across from angle B over here, but I haven't made angle B because I don't know how big it is. Excuse me. And then we know side A. So whatever side A is that I'm going to connect right here across from angle A, we know that it's not bigger than side B, or else we would have just gone to that first situation and concluded one triangle. And we know angle A is acute, or else we would be in one of those other situations. So I just want to remind you, when we first discovered the law of sines, we talked about how to find this perpendicular distance, this altitude in the triangle, okay, or this height right here. Okay? And we talked about how for that height, okay, we could use angle A, and we could set up this equation that says the sine of angle A equals opposite, which in this case is h, over hypotenuse, which is b. Or in other words, h is equal to b times the sine of angle A. So how do we know when we're going to have no triangle? We're going to have no triangle when we cannot complete this height distance right here. That there's no way we can get from this point on side B down to some point along this side. Now, the shortest distance would be to go perpendicular. That's our h. So we would know if our side A was less than H, say this was our side A, see how it's too small and it can't make that distance? So if side A is less than the height, now again, the height we defined right here to be B sine of angle A. So if the side across from the angle, that's our A, is less than the other side length times the sine of the angle, we have no triangle, okay? All right. To build exactly one triangle in this situation, again, we have the same setup. We have angle A. We have side B across from angle B. This angle at angle A is set, so we can't change it. And we know that this distance is some value of H. Okay? Well, to build one triangle, exactly one triangle, that would mean that we have just enough side length to go from that end of angle B down to just one specific spot on this opposite side, which would be the perpendicular spot. If it was longer than that, we could place it at different angles, which we'll see in a minute, that would actually make two triangles. So if side A was exactly the length of that perpendicular height, we would be able to build one triangle, and it would be a right triangle. Or we would be able to build one exact triangle. So we have side length A being equal to the height allows us to build exactly one triangle. Okay? The two triangle situation then is what if we have a longer length to deal with? So again, we have a distance B that's going unchanged. We have an angle A. Remember that this angle is set and that the minimum distance to build the triangle would be this height right here. So what if our side A is longer than that height? But it's not longer than side B, because if it was longer than side B, we wouldn't be analyzing this situation. We already know there'd be exactly one triangle. So if side length A is slightly longer than the height, so that if you set it down on top of the height, it'd go down here and go past it, that means we're going to have to put it at an angle to make the triangle. And it can either go this way, or it can go this way. So we could lay side A here, or we could lay it here, which means there are actually two triangles we can build if that side length A is greater than the other side length times the sine of angle A. Okay? So notice in all of these that A, side length A, is being compared to B sine A. Now instead of remembering the formula, try to remember that this little a is the side across from the given angle, and it's being compared to the other given side times the sine of the given angle, because they could change the letters on us, okay? All right, so this means each time we do a problem, we're going to go through this process of analyzing what is really going on. All right, so here we have angle A is 42, side A is 13, and side B is 16. So let's think about what we thought about before. The first thing I'm going to check is, did they give me a side across from an angle that's bigger than the other given side? And the answer here, no. Darn. Okay, because if that was true, I know I'd have one triangle. The next thing I'm going to look at is if the angle's greater than or equal to 90, because if it is, then that has to be true. Otherwise, I don't have a triangle. The angle's not bigger than or equal to 90. So then I move into the third situation where I need to compare the side across from the angle to the other side times the sine of the angle. Okay? So I'm comparing 13 to 19 times the sine of 42. Okay? So I'm going to take my calculator and I'm going to calculate the sine of 42. So make sure it's in degree mode, and I'm going to calculate sine of 42 times 19. And this gives me 12.7. And I'm comparing that to 13, which means it's bigger. This means that side length is in that situation where it's longer than the distance needed to make one triangle. Therefore, it makes two triangles. Okay? So, again, the general idea was they gave me this information. Here's angle A, it's 42 degrees. Here's side B, it's 19. And then I had to put side A down that was 13 units long, and now what I'm seeing is it could go like this, or it could go like this. Okay. So what I'm going to do is look at both of those triangles. So I'm going to draw them over here. And so angle A is 42 degrees, side A is 13, side B is 19. That makes the other one I'll call C. But then there's also this other situation where A is 42 degrees, side A is 13, side B is 19. That makes that angle B, and side C. So I actually have to solve two different triangles. So I have a large answer here that I'm going to be looking at. Now, when I go to solve the triangle, you might think, like, where do I start? Well, we're going to start with the law of sines, but let's notice the setup for each problem. Okay? Whether I start with this triangle on the left or the one on the right, notice that the ratio that we have is that angle of 42 is across from side of 13 in both of these. Okay? So both of these triangles have the sine of 42 degrees is across from 13, and that angle B is across from the side of 19. Okay? That's weird because angle B in this triangle is obtuse, whereas angle B in this triangle is acute, but the same law of sines equation is set up for both triangles. So I'm going to solve this and see what I get. So this is going to be 19 times the sine of 42 equals 13 times the sine of angle B. I'll divide that by 13. So I'm going to have the sine of angle B equals all of this. And then to find angle B, I'm going to have to take the inverse sine of what I get from that calculation. So I'm going to do 19 times the sine of 42 divided by 13 and take the inverse sine of that calculation, which gives me 78 degrees. We'll go to the nearest degree. Okay, so I got angle B is 78 degrees. Okay? That is not true for both of these triangles. Again, in this triangle here, angle B is obtuse. Okay? So that 78 degrees has to go with this triangle right here. Okay? So what I know is that in this triangle, angle B is 78 degrees, which then makes angle C equal to whatever 78 plus 42 subtracted from 180 is. So that makes angle C equal to 60 degrees. And then to find side length C for this triangle, I would set up my trig ratio again. So I have sine of 42 over 13 equals, and since I now know this is 60 and I'm trying to figure out this angle across from it, the sine of 60 over C. And then I could use this equation to solve for C, and we'll solve side lengths to the nearest tenth. So I'm going to do 13 times the sine of 60, and that's going to end up being divided by the sine of 42. And so I get a side length of 16.8 for side length C. So here is one of the triangles. Okay. The other triangle is what I have over there, but I feel stuck because I tried to find this angle B using the law of sines, but I know 78 is not correct because angle B is obtuse. So what I want to do is bring your attention back to the drawing that shows both of the lines together. So in one of our triangles, here's angle B, the obtuse angle. And in another triangle, here's angle B, right here, this acute angle. Okay, and that's the one we found to be 78 degrees. Notice that right here, like a geometry problem, if I look at both of the lines drawn, both side A's drawn into the triangle together, they create their own little isosceles triangle, which means if this angle is 78, so is this one. And that the obtuse angle B that I'm looking for, with that 78 near pair, they make 180 together. So I'm going to do 180 minus 78, which gives me 102 degrees, and that's what this angle B is over here. Okay? So for this triangle, angle B is 102 degrees, okay, which then makes angle C equal to 180 minus that 102 plus 42, which is 36 degrees. And now that I have a different measurement for angle C here than I had over here for 60 degrees, I can set up the law of sines again to find angle or side length C in this triangle. So I'm going to be looking for the side length C. So I would have the sine of 42 over 13 equals the sine of 36 over C. And I would solve this for side length C. So I would do 13 times the sine of 36 divided by the sine of 42. And I would get that side length C is equal to 11.4, which makes more sense for this triangle because it's the across from the most acute angle. So side length C here is 11.4, and this is the solution for that triangle. Okay? So there are two triangles here. Or two solutions. And I would have to list both of them, which means this answer as well as that answer. Okay, so it's patience and work that's going to help you get through this process. Okay, so if we look at the next one, okay, again, I would go through the process. Is side length A greater than side length B because it's across from the angle? No. Is angle A bigger than or equal to 90? Because if so, that should have been true, or I don't have a triangle. No. So then again, I'm going to compare the side across from the given angle to the other side length times the sine of the angle. So in this case, that's 2, should be compared to 10 times the sine of 50. So on my calculator, I would figure out 10 times the sine of 50, which is 7.7. And when compared to, 2 is less than 7.7. This means my side length A across from the angle is not long enough to meet the minimum height requirement to build a triangle, which means here there is no solution. There is no triangle that can be built according to those specifications. I'm going to look at one more here. Okay, so notice here they gave us A and B and C. Okay, so I'm having a little bit of a hard time understanding that. So if I draw a picture of this, if angle A is 67, say I call this B and C, then side length B is 13 and side length C is side length B is 35 and side length C is 47. So I feel pretty certain one triangle could be built here because I can make this side length whatever I want to complete the triangle. So I don't need the analysis, but I actually cannot solve this problem because if I try to set up a ratio using an angle and the side across from it, the only angle I have, I don't have the side across from it. So at this point, I would be stuck. Okay? But in honest truth, it's not that there's no solution. I know I could build a triangle like this. It's that I don't have a tool right now to find the different side and angle measurements. So I'm just going to leave a note right now, and we're going to discuss this further on Wednesday. How do I find these measurements? So it seems like the law of sines, though helpful, doesn't help us in every situation, and we have to find something else that can in these areas. So that's what we're going to work on. Okay? There are some try these problems in your note guide if you want to go through a couple of them, or you can start the law of sines homework. That way you can come in with good questions for Wednesday. Remember, Tuesday we're planning on doing your stat report.